What's up, my pre-calc people? I'm Michael Precalculus, and in this video, we're going to do a quick review of Unit 1 for AP Precalculus. Now, Unit 1 covers polynomial and rational functions, and it's an absolutely enormous unit with tons of topics, tons of problems, and tons of vocab. But we're not going to cover all the teeny tiny details in this video. I'm just going to hit the big ideas and the big concepts that are going to enable you to pass the AP Precalculus exam in May. All right, so let's dive into all those big ideas and big concepts right now. So Unit 1 is primarily over polynomial and rational functions, but what it explores in Unit 1 is all about change, how these functions change. So we really want to focus on general characteristics of functions, exploring how function values change as the input values change. And there's tons of topics that we can examine here. Now, the first big topic is the zeros of a function. The zero of a function is a value of x that produces an output of 0. This occurs where f of x equals 0. Like literally set your function equal to 0 and solve. These are called solutions. They're also called x-intercepts. Now, if we have a graph, it's pretty easy to just visually look and see where we have those x-intercepts. So we see we have one here at -4 and one at 0. Very, very simple to see where we cross the x-axis. Those are our solutions or our x-intercepts. Now, if we don't have a graph and we actually have a function, then what we need to do is set it equal to 0. So the first step I would do here is set it equal to 0, and then I would begin to solve. Now, how do you solve, especially when you're working with a polynomial function? Factor first. Once it's in factored form with the 0 over on one side, you could use the zero product property. So x plus a could equal 0, which means x equals -a. X minus b could equal 0, which means x equals b. So it's very easy to find your zeros once you're in factored form. Now, if you're a rational function, to find zeros, we tell you to focus on the denominator. Or, excuse me, I said that wrong. Focus on the numerator, because when the numerator is equal to 0 is where you have zeros. But there's a huge asterisk to that, unless you also make the denominator 0. Because if you're a value, like -a in this problem, -a makes both the numerator and the denominator equal to 0, that's going to produce a whole, not a 0. So in this case, x minus b comes from the numerator. It could equal 0, which means my only 0 is going to be x equals b. From the denominator, this thing right here is going to create a vertical asymptote. And again, if you make both the numerator and the denominator 0, you're not a 0, you're a whole. So be very careful when you're looking at rational functions and exploring zeros. The next thing we like to take a look at when we're exploring functions is where those function values are positive, where function values are positive. Now, this is basically saying where is your function greater than 0, because a number greater than 0 is a positive number. Graphically speaking, we're looking at where is the graph above the x-axis. So if we have a graph, all we got to do is open our eyes and look, where is the graph above the x-axis? It's going to be anywhere from -infinity to -4, and then anywhere from 0 towards infinity. Those are the two spots where we see that the function is above the x-axis, hence greater than 0. Where are function values negative? Well, we're talking about function values being negative. We're certainly talking about them being less than 0, because being less than 0 means you're a negative value. Here we're looking at below the x-axis. So if we go back to our graph, we're looking at values that are below the x-axis, which would be from -4 to 0. All of these values here would produce output values that are negative. Now, if we don't have a graph and we're asked to figure out where a function is greater than or equal to 0, or greater than or equal to 0, or just greater than or just less than, then we got to do a little bit of work. So if we're looking for where this function is greater than 0, well, we're just simply going to say, okay, where is the function greater than 0? So we're going to take x plus a times x minus b, and we're going to set it greater than 0. Now, if you're not already factored, factor it. That's what you need to do first. Then what we have to do is we got to get our solutions if it was an equation. So again, that would be x equals -a, and that would be x equals b. Then what we do is we create a number line. We put these values in order on that number line, and then we have to test values out. So we pick a value down here below -a, we plug it into our function, and we determine, do we get a value greater than 0? If so, that's a good thing. Or do we get a value less than 0? If so, that's a bad thing. So again, we're doing our test intervals. We're going to test the value here, test the value here, test the value here, and see what happens. Where are we positive? Where are we negative? Because that's where we're going to find our solutions. Now, with a rational function, we might do the same thing. Hey, where is this function less than 0? Once again, we're going to take the function x plus a times x minus b divided by x plus a over x plus c, and we're going to make it less than 0. Now, any value that makes the numerator or the denominator equal to 0 is going to need to go on that number line. So again, anything. So we're going to have our negative C, or excuse me, our negative A, our negative C, and our positive B. Again, put them in order. Right now I'm just being generic with A, B, and C. And then you have to test all of them out and determine what interval creates values less than 0. Overall, not too bad, but keep in mind at negative A, there's a hole. So that's actually now they're going to be positive or negative. You don't want to include that either. At negative C, we're going to have a vertical asymptote. So there's nothing there either. You can't be positive or negative. Now at B, we're actually equal to 0. So it's going to be open if it says less than 0, or we could fill that in if it said less than or equal to 0. But again, it's all about finding those solutions and then creating that number line to test out your intervals. All right, now the next important thing that we could talk about when we're analyzing a function is where that function is increasing. A function is increasing over an input interval a to b if its domain, as the input values increase, the output values also increase. So graphically speaking here, we're talking about the function going up. So from a to b, we're going up, which means any value of f of b is going to be greater than a value of f of a, hence we're increasing. Now, if we're looking at a graph, this is very easy to see where we're increasing. So if I follow here, I'm definitely decreasing, and then starting here at negative 2, I'm increasing, I'm increasing, I'm increasing. Oh, I'm still increasing, I'm still increasing, I'm still increasing. So my interval for where I'm increasing would be negative 2 towards infinity. All of the values to the right of negative 2 are going up. Now we can also talk about decreasing. A function is decreasing. Whoa, I have a typo there. That should say decreasing right there. Sorry. A function is decreasing over an interval a to b of its domain if, as the input values increase, the output values always decrease. So here we're talking from a to b, our values are going down, meaning that any value of f of b is less than a value of f of a. Now, when we look at a graph, all we got to do is look. Where do we see the function values going down? And we see that that's going to happen here to the left of negative 2. So any value from negative infinity way over here up to negative 2, our values are decreasing. Pretty easy to see when we look at a graph. Now, another important characteristic of functions are the maximum and minimums. These are also called extremas. Extrema is just another fancy word for max and mins. Now we have different types. We have absolute extremas. These are one values that are absolutely larger than every other value or lower than every other value. So if you're going to call something an absolute extrema, there could be nothing above it if it's a max or nothing below it if it's a min. Now, a relative extrema means relative to a particular interval, it is the highest value or the lowest value in that region. Now, we got to be extra careful here because over a closed interval from a to b, the endpoints are considered extremas. So let's look at this graph real quick right here. First, we notice that we do have what would be considered an absolute minimum. This value right here is absolute. There's literally absolutely nothing lower than it. So that would be considered an absolute minimum. There's nothing below it, or an absolute extrema. But here's what I want to point out when I'm talking about an interval. Let's just say that we were looking at an interval and we said, all right, if we're going to look at an interval from negative 6, which is, let's do negative 5. Negative 5 from right here to 0. So if we're going to look at that interval, so let me actually highlight that. There we go. In that interval, we could say, how many extremas do we have? Well, there's actually 3 extremas. Down here, there's an absolute minimum. So we definitely see this absolute minimum right here. But this value right here and this value right here would be considered extremas as well, even though they're endpoints. Because remember, we're ignoring all other parts of the graph. So that means that this point right here would actually become an absolute extrema. It is the highest point of all the points in that interval. And this right here would be, well, we'd call that a relative maximum. Now, there are plenty of other values in the interval, namely these over here, that are all higher than it. But relative to its general vicinity, it is an extrema in its areas. That's why we call it a relative extrema. So you got to be really careful when we talk about inputs and we're breaking down a graph like that. All right, now the next big concept is concavity. When we're talking about the concavity of a graph, we're examining how a function is changing over an input value interval. So the graph of a function is concave up on intervals in which the rate of change is increasing. The graph of a function is concave down on intervals which the rate of change is decreasing. Now, this concept of concavity can be very tricky for a lot of students, so I'm going to do my best to explain to you right now. So here we see a portion of a graph. Now we're only looking at a portion ranging from A to B. Okay, now what's happening here? Well, let's talk about function values first. If we're talking about function values, they are decreasing. We see that as we move from A to B, the values are going down. That's pretty obvious. Now, what about, are they positive or are they negative? Well, they're all above the x-axis, so they are all positive. Again, they're above the x-axis, positive. Come on, simple. But now let's talk about the rate of change, because that's what concavity is about, the rate of change. How are we changing? Now, what's happening here is so notice that we're decreasing. So if we think about our rates of change, how we're changing as we move throughout this function, we're negative. All of our rates of change are negative. So when we say that the function values are decreasing, that means the rates of change are negative. The rates of change are negative because if I'm a point and I go to another point and another point and another point, my rates of change between those points are going down, hence negative. But how are they going down? Well, they're going down at an increasing rate. Well, let's think about that for 1 second. They're negative, right? So they're actually going down at a decreasing rate because they're becoming more and more and more negative. Again, more and more and more negative. So here is my first rate of change. It's negative. Here's my second rate of change. It's negative. Here's my next rate of change. It's negative, but they're more and more negative. Hence, concave down. So the rates of change are decreasing. They're getting more and more negative, right? They're going down. They're getting more and more negative, which means we're concave down. So that's the idea of concavity. It's tracking how we're changing. So concave down. And again, once you get the idea of concavity, you can almost see it. Like, look, it's concave down. Look at the concavity of that graph. All right, let's check out this one right here. All right, once again, let's explore what's happening from A to B. Now, if we're looking at function values, oh, they're increasing. How cool. They're going up. That's pretty obvious. And they're also positive. The function values are positive because they're all above the x-axis. But what about the rates of change? All right, the rates of change at each point as we move throughout this graph are positive. All of those rates of change are positive. So when we say that the function values are increasing, that means that the rate of change throughout them is positive. But how are they changing? Well, here it's really positive. Here it's less positive. It's still positive, but it's less positive. Here it's, again, still positive, but less positive. So the rates of change are decreasing. Yes, they're staying positive, but they're getting less and less positive, so the rates of change are going down, which means I'm concave down still. And again, if you understand concavity, when you make that graph, you say, oh yeah, it's concave down. All right, now let's check out this graph. Once again, we're looking at A to B, and now we say, okay, what are the function values doing? Well, they're decreasing. We clearly see that as we move from left to right, our values are decreasing. But they're also negative because they're all below the x-axis. All right, what about the rates of change? So once again, let's explore some points as we move throughout, and we see that the rates of change are negative. Okay, so the rates of change are negative, and that's of course, well, I can't spell negative today. That's of course because we're decreasing. Now, how are they changing? Well, they're actually getting less and less negative. Here is we're really negative. Here we're still negative, but less negative. Here we're, again, negative, but less negative. So our rates of change are actually increasing because they're becoming less and less negative, and that's concave up. One more graph here, another graph. Okay, what's going on here from A to B? Well, we're increasing. Clearly, the graph is going up, increasing. Now, it's actually half positive and half negative. Some values are above, some values are below. We even actually have a 0 right there as well, where we're not positive or negative, we're equal to 0. But now let's talk about rates of change. Well, as I move throughout this graph, my rates of change are all positive. That's because the graph is increasing. So the rates of change are positive. That's awesome. But notice what's happening. They're becoming more and more positive. So right here, I'm positive, more positive, more positive. So my rates of change are increasing. They're going up. And again, concave up. So when we talk about concavity, we're talking about how are your rates of change changing. If your rates of change are getting bigger, more and more and more positive, or less and less negative, you're concave up. If your rates of change are decreasing, becoming less and less positive, or more and more negative, then we're concave down. Okay, And anywhere where we change concavity, maybe you switch from concave up to concave down, that's going to be called an inflection point. Now, when we look at a graph, we can also see concavity. So we see here we're concave up. At this entire graph, I'm concave up. So my rates of change are negative, and then they become positive. But they're constantly increasing. They're really negative, not so negative, less negative, and then now they're positive, more positive, more positive. So that's why I'm concave up. Now, over here, I'm linear. When you're linear, you're neither concave up nor concave down because your rate of change is constant. And then this last piece right here is concave down. Let me show you this right there. That piece right there is concave down. Because as I find or analyze my rates of change, they're becoming less and less positive. They're positive throughout. It's increasing, so the rates of change are positive, but they're less and less positive. That's why it's concave down. So hopefully you understand this idea of concavity. It's just a matter of examining the graph and seeing what's happening to your rates of change. But we also have to consider what's happening to our function. So we have these two words, positive, negative, increase, decrease. So I guess that's 4 words. And how we use those words depends upon how we're talking about the function values versus talking about the rates of change. So hopefully that's a pretty good explanation for analyzing concavity. It is a pretty good concept, but I wanted to give a quick overview of it in this video. Speaking of rate of change, how do you find the average rate of change over an interval from A to B? Well, it's actually quite simple. The average rate of change is just a fancy way of saying the slope. So to find the average rate of change, all we got to do is take the output of the second point minus the output of the first point divided by the input minus the input. Pretty easy. So not too bad. So the average rate of change over the closed interval A to B is the slope of the secant line from the point A, comma, f of A to B, comma, f of B. All right, let's use a graph to kind of make this really, really simple. So imagine we have 2 points here, and I'm just going to kind of grab 2 random points. So we have this point right here. We'll call that point A, comma, f of A. And then we have this point over here. We'll call this point B, comma, f of B. Now, if we connect these 2 points with a line, and again, sorry for my crappy line here, it's actually not too bad. Well, the slope of that line is the average rate of change between those 2 points over the interval A to B. And we call that line a secant line. So the slope of the secant line is the average rate of change between those 2 points. Pretty simple. And again, how do you find that average rate of change? All you got to do is take the f of B minus f of A, doing subtracting your outputs, divided by B minus A, subtracting your inputs. Quite easy, not overly difficult, and, well, pretty simple to understand. All right, now let's talk more specifically about rate of change with 2 different types of functions, linear and quadratic. All right, what we learned in this unit is that linear functions have a rate of change that is constant, meaning the average rate of change between any 2 input values is the same, hence a constant value. So if we take a look at this input-output table, and let's just grab, again, it says literally any 2 points. So let's use this first point, 0, 2, and this point, 9, 11. So if we find the average rate of change between those points, we're going to do 11 minus 2, subtracting the outputs, and 9 minus 0. Well, 11 minus 2 is 9, 9 minus 0 is 9, so my average rate of change is 1. Now, grab any other 2 points. So let's grab this point right here, 1, 3, and this point right here, 16, 18. So once again, subtract the outputs on top, 18 minus 3. Subtract the inputs in the bottom, 16 minus 1. And let's see here, 18 minus 3 is 15. 16 minus 1 is 15, and the average rate of change is 1. So that's how we know this is a linear function, because if you take any 2 input values and you find the average rate of change, it's going to be a constant value. In this case, that constant value is 1. Now, with quadratic functions, a little bit different. For a quadratic function, the average rates of change over consecutive equal-length input value intervals could be given by a linear function. Now, what's most important here is we can't just grab any 2 points. We have to grab consecutive equal-length input value intervals. And over consecutive equal-length input value intervals, we see that the rate of change is changing by a linear value. So here we do have, in this table, we do have consecutive equal length input values. So the length is 2, and they're consecutive. 0 to 2, 2 to 4, 4 to 6, 6 to 8. Pretty simple. So if we look at the difference, the change, right, we're going up 3. Then we're going up 4. Then we're going up 5. then we're going up 6. So it's obviously not linear because we don't see a constant rate of change. We see a rate of change that's, well, changing. But how's it changing? Well, the rate of change, our second difference is plus 1, plus 1, plus 1. So because the second difference is constant, meaning that our rate of change, our change is linear. That's exactly how we know that this is a quadratic function. So again, that's what we learned as well. All right, the next characteristic is really, really important, and that is the end behavior of functions. Now, what we learned for the first time in AP Calculus is how to explain or notate the end behavior of a function using what we call limit notation. So the end behavior of a function is what happens as x increases without bound, meaning x is going towards infinity forever and ever, or x decreasing without bound. So now when we allow x to increase without bound, we're talking about the right end behavior. And when we decrease without bound, we're talking about the left end behavior. Now the way we notate that is with the limit. So we say the limit as x increases without bound towards infinity of our function. So we're looking at that right end, and well, what's happening? Is it going up forever towards infinity, down forever towards negative infinity, or maybe it's approaching a specific value that we have based on a horizontal asymptote? And the same thing with the end behavior as x decreases with bound. So it's really important that you understand, A, how to notate this, because that's what's going to be asked of you on the AP exam. Now, let's look at an example here. So if we have a graph and we're saying, all right, what's the end behavior of this graph? We're going to look at the right end. So as x goes towards infinity, notice the function is also going towards positive infinity. Pretty simple. Then we're going to look at the left end. As x goes towards negative infinity, the function is going down towards negative infinity as well. So that would be the specific end behavior for this graph. Now, what if we don't have a graph? Well, for polynomial functions, we could determine the end behavior by examining two things: the degree of the polynomial and the positivity or negativity of the leading coefficient. So first, if your degree is even, if you have an even degree, 2, 4, 6, 8, then that means both ends are doing the same thing. Either both ends are going up or both ends are going down. Now, how do you know which one it is? Well, that's where you have to look at the leading coefficient. If the leading coefficient is positive, both ends are going up. If the leading coefficient is negative, both ends are going down. Now, when you have an odd degree, 1, 3, 5, 9, then you have to look at the idea that one end is doing the opposite of the other end. So either one end is going up and the other end is going down. Well, that's a bad arrow. Or one end is going up and the other end is going down. Could be vice versa. Now, how do you know which one it is? Well, again, you have to look at the leading coefficient. If the leading coefficient is positive, the right end is going towards infinity. The left end is going towards negative infinity. If your leading coefficient is negative, the left end is going towards positive infinity. The right end is going towards negative infinity. So it's pretty easy to see that when you have a polynomial. Even when you don't have the graph of the polynomial, you can still determine the end behavior of the function. Now, how do you find the end behavior of a rational function? Well, all we got to do is divide the leading terms. That's going to be the key to telling us about that end behavior. And actually, it's going to tell us a lot more, too, that I'm going to describe. But again, these are the leading terms. We got our coefficients with the x raised to the biggest powers. In this case, I'm just being generic with n and m. Now, there are three different possibilities when you divide your leading terms. The first possibility is that the resulting quotient is a rational function. So when you divide your leading terms, the leading coefficients a and b are there, but then you had more x's in the denominator, so that way you still have an x left over in that denominator. Now, what this means is that there is a horizontal asymptote at y equals 0. That's the x-axis, guaranteed. And this means that both ends and behaviors are going to approach 0. So as x goes towards infinity, the function is going to go towards 0. And as x goes towards negative infinity, the function is going to go towards 0 because it's going to suck into that horizontal asymptote. Now, the second possibility is that the resulting quotient, when you divide those leading terms, is that you get a constant term. That means that your degrees were the same, and hence your x's reduced or canceled out. So all that's left is the leading coefficients of a and b. If this occurs, that means you have a horizontal asymptote at y equals a over b. And the end behavior towards both sides is a divided by b. So the limit as x approaches infinity is going to be equal to a over b, and the limit as x approaches negative infinity is also going to be a over b. It's going to be the same on both sides. Now, a third possibility is that the resulting quotient is a polynomial. So here we're going to get our leading terms, our leading coefficients, a over b, but then we had a higher degree in the numerator, so we left an x raised to the d in the numerator. Now what this means is that we have no horizontal asymptotes whatsoever. And this tells us that the end behavior of the original rational function will match the end behavior of the resulting polynomial function. So then we got to go back to our rules about how to know the end behavior of a polynomial function. Even degree, odd degree, positive or negative leading coefficient. So once you follow those rules, whatever the end behavior of this resulting polynomial function is going to be the same end behavior for the original polynomial function. Now, there's also a special case here. If the resulting quotient isn't just any polynomial, it's a linear polynomial, that means we have x to the first. That means that the numerator degree was 1 bigger than the denominator degree. This means that there is still no horizontal asymptote, but there is a slant, or also known as an oblique asymptote. Now, the slope of that slant asymptote is the same as the resulting linear polynomial a over b. So when we get this linear polynomial, when we divide our leading terms, that slope of that linear polynomial, a over b, is going to be the same slope of our slant asymptote. So that's another important characteristic to make sure we know as well. Now, let's continue talking about rational functions since we're on the topic. Rational functions, some of the most important characteristics of them are zeros, wholes, and vertical asymptotes. Let's talk about how to identify those. Now, here is a generic rational function that's in factored form. If you always factor your rational function, it's going to make it a lot easier to find all of this information. So first, a zero of a rational function is a value that only makes the numerator equal to 0, not also the denominator. So in this particular case, that would be this factor right here, x minus b. Therefore, we're going to have a 0 at x equals b, because b minus b creates a 0 in the numerator only. Yes, we have an x plus a of an x plus a, but that makes both numerator and denominator 0. That's going to be something else that we're going to talk about right now. So that's when a whole gets created. A whole occurs at an x value that makes both the numerator and the denominator equal to 0. So in this case, we're going to be seeing those common factors, x plus a over x plus a. That means we have a whole at x equals negative a. Now, that's the location of the x value of the whole. How do we find the y coordinate of that whole? Well, we simply take that value of negative a that we got right here, and we ignore these terms, because technically they're going to get removed, and we plug negative a in to what is left. So we do negative a minus b on top, negative a plus c on the bottom, and that value right there is going to be the y coordinate of where our whole is. Now, basically we're finding the coordinates of the whole, but there's really nothing there. So it's the coordinates of an empty spot is basically, but that is an important thing that you could be asked to find. Now, lastly, a vertical asymptote occurs at an x value that makes only the denominator equal to 0, not also the numerator. So in this particular case, that's going to be the x plus c, because negative c is going to create the denominator into a 0 and not also the numerator, because once again, remember, if you make both numerator and denominator 0, you're going to be a whole. So in this case, we have a vertical asymptote at x equals negative c. All right, now one of the final topics of Unit 1 is transformations of functions, all the different ways that you could take a function and transform it. We got dilations, translations, and we have dilations. So here is a generic model of how we could take a function and transform it. We got 4 different values. We got a, we got b, we got c, and we got d, all these different locations that are going to tell us different things. So let's talk about each one of them right now. First, a, multiplying out in front of your function, is a vertical dilation by a factor of a. So if you're going to have a 3 there, you're going to multiply your outputs by 3, and that's going to be a vertical stretch. If it's like a 1/2, that's going to be a vertical shrink. Now, if a is negative, that doesn't affect the vertical dilation. What that's going to do is that's going to cause reflection across the x-axis. Then we have the d value. The d value on the end over here, this is a vertical translation. That's a slide. And it's going to slide us by whatever d is. So if a, so if there's a positive d, there kind of gets confusing. But anyway, if there's a positive d, that's going to translate you up d units. If there is a negative d, that's going to move you down d units. So it holds true to what it says. Plus d, you go up. Minus d, you go down. Then we have the b value. The b is going to be a horizontal dilation. this is multiplying inside of your function. Now, this is going to be where it gets a little bit tricky. So we have a horizontal dilation by a factor of 1 over b. So it's not b, the factor is 1 over b. So for example, if we have a 2 in there, we're actually going to be a horizontal shrink because that's going to multiply us by 1/2 for our x's. Now, if b is negative, that doesn't affect the dilation. What that's going to do is that's going to cause a reflection across the y-axis. And then finally, we have c. C is the addition or subtraction of a constant inside of the function. This is going to be a horizontal translation, that's a slide left or right, by negative c units. So what that means, negative c units, is that if you have x plus c, that's going to actually move you left c units. And if you have x minus c, that's going to move you right c units. So it's kind of opposite of what it says, and that's why generically we say that it's going to move you negative c units. So if a plus c, you're going left. If it's a negative c, you're going to do a negative of a negative, which is a positive, move you to the right. All right, so let's look at a quick example of exactly what I'm talking about here. So here we see a function g that is defined by taking a function f, multiplying it by 3 on the outside, adding 7 on the outside, multiplying by 2 on the inside, then adding 5 on the inside. All right, so what all do we see here? So the first thing I see is that vertical dilation by a factor of 3. That's right there. That's going to multiply my y values by 3, making it a vertical stretch. Then we see a vertical translation 7 units up. This is the plus 7 on the end. That's going to move me 7 units up. It's going to take the whole function collectively up 7 units. Then we have that b value of 2. That's going to be a horizontal dilation by a factor of 1/2. That's actually going to be a horizontal shrink. Now I'm going to be smaller. And then finally, we have that plus 5 right here. That's going to be a horizontal translation left 5 units because it says plus, but that means it's actually going left 5 units. Now, if we were to look at this as a point, we think about the original point from f of x, that is x comma y. X goes in, y comes out. But what would the new points look like for function g after these transformations? Well, let's do the y's first. So we're going to multiply by 3 and add 7. That's that vertical dilation and vertical translation. So our new y is going to be 3y plus 7. What about our x's? Well, we're going to have that horizontal dilation by a factor of 1/2. So we're going to multiply by 1/2. And then we're going to move it left 5 units. That's going to be that minus 5. That's going to take us left 5 units. All right, hopefully that makes a lot of sense. That wasn't too complicated. All right, now the final thing I'm going to talk about is solving equations. So I'm going to tell you right now, multiple times on the AP exam, you're going to be asked to solve some equations. Now, for example, let's find all values of x such that f of x equals 6. They give you a function f of x, and they want to know all values where that function equals 6. I got 2 ways that you could do this. 1, no calculator, no problem. All you got to do is set up the equation and solve. You guys should know how to solve an equation by now. So we're going to take that function, whatever it is. Maybe it's logarithmic, maybe it's exponential, maybe it's a polynomial, maybe it's trigonomic. Who knows? Maybe it's just basic polynomial, and we're going to set it equal to 6. We just got to use all of our solving techniques. Hopefully you've learned all the different ways to solve. Now, if it's a polynomial, then we should get everything on one side. That way we have a 0 on one side and factor. That way we can use a zero product property. But you guys should know how to solve equations by now. Now, the second option is if you have a calculator, and if you do, I'd recommend using it. So how would I solve this equation if I had a calculator? I wouldn't waste any time trying to do all the work by hand. I would go to y equals on my calculator. In y1, I would type in 6, the right-hand side. In y2, I would type in f of x, the original function they gave me, the left-hand side. Now, obviously, you could switch the order of that. It wouldn't matter whatsoever. And then hit graph. Now, I would recommend starting off with a zoom standard. That's a 10 up, 10 down, 10 left, 10 right. And then what you're going to look for in the graph is the intersection point of these two functions, because where they intersect is, well, where they're equal. And then all you have to do is use the trace command on your calculator to find that intersection point, and boom, you got your answers. So pretty easy there to solve equations. Shouldn't be too difficult. All right, that's it for Unit 1 quick summary review. I know there's a lot in Unit 1 that I didn't cover, but I just tried to hit the big points that I know are going to come up on the exam. Good luck studying.